Hello everyone, welcome to the lecture. Myself Devananda Rao, working as Associate Professor in the Department of CSC, MLR Institute of Technology, Hyderabad. Today's topic is DFA example problems. Construct a minimal DFA which accepts set of all strings over 0, 1 which when interpreted as binary number is divisible by 2. So, binary number, if a number is divisible by 2, suppose if you divide any number by 2, we will get a reminders either 0 or 1, 0 or 1. So, 1 divided by 2, if you take 1, its binary number is 1, divided by 2, 1 is divided by 2, we will get remainder 1. Suppose 0, binary is 0, divided by 2, remainder 0. So, if you divide any number by 2, you will get reminders 0 or 1, remainder 0 or 1. So, we need two states, one is remainder 0 state, because divisible by 2 means remainder 0, any number divided by 2 means remainder 0. So, that remainder 0 state is the initial state, another is remainder 1 state, remainder 0 states, which number if 0 divided by 2, 0 is divided by 2, remainder is 0. Another is 2, that is binary number of 2 is 1 0, divide by 2, remainder 0. 4, 1 0 0, this is 0, this is 2, this is 4, then 6, 1 1 0 is a 6, then 8, 1 0 0 0. So, if you divide 0 by 2, remainder 0, divide 2 by 2, remainder 0, divide 4 by 2, remainder 0, divide 6 by 2, remainder 0, divide 8 by 2, remainder 0, like that and so on, 10 by 2, remainder 0. Remainder 1 state, 1, binary number is 1, 1 divided by 2, remainder 1, then 3, binary number is 1 1, then 5, 1 0 1, then 7, 1 1 1. So, 1 3 5 7 9 like that, divide by 2 will get remainder 1. So, in initial state if you read 0, stay in the same state because 0 is remainder 0. If you read 1, that means 1 binary number is 1, if 1 divided by 2, remainder 1, I will go to non-final state. So, we have defined a transition function for state A for 0 and 1. We have to define transition function for B also for 0 and 1. If you read 0 in B, that means previous symbol is 1, current symbol is 0, that is 1 0, that is 2, 2 by 2, remainder 0. So, that in B if you read 0, go to remainder 0 state. That means if you read 1 in B, that is previous symbol is 1, current symbol is 1, that is 3, 3 by 2, remainder 1. So, that stay in the same state. Like that any combination 1 0 1, that is 5, 5 by 2, remainder 1, that is initial state, first symbol is 1, from initial state by reading 1 I can go to B, next symbol is 0, I go back to A, next symbol is 1, I go to B, that is B is non-final state, remainder 1 state, like that. If you take 1 1 1, start with A, 1 go to B, 1 stay in B, 1 stay in B, like that. This diagram will work for any binary number divisible by 2. Example, construct a minimal DFA which accepts set of all strings over 0, 1 which when interpreted as binary number is divisible by 2. So, if you divide any number by 3, we will get 3 reminders. Remainder 0, remainder 1, remainder 2. Only possible reminders 0, 1, 2. Then 0, if you take 0 number, that binary number is 0. 0 by 3, remainder 0. If you take 1, binary number 1. 1 divided by 3, remainder 1. If you take 2, that is binary number 1, 0. 2 by 3, remainder 2. Next, if you take 3, binary number is 1, 1. 3 divided by 3, remainder 0. Next, 4, binary number 1, 0, 0. 4 by 3, remainder 1. Next, 5, binary number 1, 0, 1. 5 divided by 3, remainder 2. Next, 6, 1, 1, 0. 6 by 3, remainder 0. 7, 1, 1, 1. 7 by 3, remainder 1. 8, that is 1, 0, 0. 8 by 3, remainder 2. Like that. 9 by 3, remainder 0. Like that. 10 by 3, remainder 1. 11 by 3, remainder 2. So that we have remainder 0 state, remainder 1 state, remainder 2 state, remainder 0 state, remainder 1 state, remainder 2 states. Initial state is remainder 0 state because any number divisible by 3, that is remainder 0 state. First 0, binary number 0. If you read 0 in A state, stay in the same state. If you read 1 in A, that means 1 by 3, remainder 1 state. So that I can go to remainder 1 state. Then in B, if you read 0, that means previous symbol is 1, current symbol is 0, that is 1, 0 is 2, so that 2 is the remainder 2 state. If you read 1 in B, that is in B state, read 1, previous symbol is 1, current symbol is 1, that is 1, 1, 1, 1 is 3, 3 by 3, remainder 0, so that I go back to remainder 0 state for 1. In C, current symbol is 0, previous symbol is 0, that means before that we have 1, 1, 0, 0, 1, 0, 0 means 4. So A to B is 1, B to C is 0, current symbol is 0, that is 1, 0, 0 is 4, 4 by 3, that is remainder 1 state, remainder 1 state. Next, in C, if you read 1, that is first symbol is 1, previous symbol is 0, that is 1, 0, current symbol is 1, 1, 0, 1, that is 5, 5 by 3, remainder 2 state, remainder 2 states. This is the transition diagram. So this diagram will work for any binary number divisible by 3. Then A is the remainder 0 state. The state A is remainder 0 state. B is remainder 1 state. C is remainder 2 state. Transition diagram A, B, C. A is the initial state and as well as final state 0, 1. A and 0 going to A and 1 going to B, B and 0 going to C, B and 1 going to A, C and 0 going to B, C and 1 going to C on. This is the transition diagram. Next, design a DFA which checks whether the given unary number is divisible by 3 or not. That means unary number, the number with only one symbol, like 1, 1, 1, 1. So 4, unary number 4 symbols. 4 is represented with 4 ones. 5 is represented with 5 ones. 6 is represented with 6 1. Unary numbers divisible by 3. So here we need to find multiple of 3 divisible by 3. Initial state, that is A, then B, then second B, next C to D, that is 1. So we have seen 3 symbols, 1, 1, 1. So 3 divided by 3. 4 symbols, that means you should not stay in the final state, go back to B. So multiple of 3, So 1, 3 ones followed by 3 ones, then 1, 1, 1. So it will repeat multiple of 3. So that this is the diagram for DFA, which checks whether the given unary number is divisible by 3 or not. Next, design finite automata with given input alphabet sigma is equal to 0, 1. Accept even number of zeros and even number of ones. Even number of zeros and even number of ones. Any string will contain 4 combination of zeros and ones. Any string will contain 4 combinations of zeros and ones. They are, first one, even number of zeros and even number of ones. Second combination, even number of zeros and odd number of ones. Next, odd number of zeros and even number of ones. Last combination, odd number of zeros and odd number of ones. 4 combinations. So that we need 4 states. So initial state is, if there is initial state means the machine will stay in the initial state, that means no symbol has read, so that no 0 number of zeros and 0 number of ones, that is initial state as well as final state. So this is even number of zeros and even number of ones, this is Q naught. So Q naught is the state for even number of zeros and even number of ones. Suppose if you read 0 in Q naught, it becomes odd number of zeros and even number of ones. That means the first symbol is 0, that means that is Q2 state. This is Q1, this is Q3. So if you read 0 in Q naught, that means zeros will become odd, even ones as it is even. So that Q2. If you read 1 in Q naught, that means Q naught means 0 number of zeros, 0 number of ones. If you read 1 in Q naught, that means ones becomes odd, zeros as it is even. So even number of zeros, odd number of ones. This is Q1. This is Q1. Coming to Q2 for defining the transition for 0 and 1. Q2 means odd number of zeros, even number of ones. If you read one more 0 in Q2, if you read 0 in Q2, that means odd number of zeros will become even number of zeros. Ones are as it is. So that if you read 0 in Q2, that means even number, zeros becomes even number of zeros. Ones are even. So that even number of zeros, even number of ones. The state for even number of zeros and even number of ones is Q naught. So I can go to Q naught. In Q2, if you read 1, that means the state for Q2, the state of Q2 is for odd number of zeros and even number of ones. If you read 1 in Q2, ones becomes odd. Zeros are already odd. So odd number of zeros, odd number of ones. State is Q3. Coming to Q1. Q1 also you need to define transition for 0 and 1. Q1 is even number of zeros, odd number of ones. Even number of zeros, odd number of ones. If you read 0, zeros will become odd number of zeros. Ones are already odd number. So that odd number of zeros, odd number of ones means Q3. If you read 0, odd number of zeros, odd number of ones. In Q1, if you read 1, what is Q1 meaning? Even number of zeros, odd number of ones. If you read 1, ones becomes even. So that even number of zeros, even number of ones. Even number of zeros, even number of ones means Q0. I can go to Q0 for 1. Coming to Q2. Q2 is the current state, that is odd number of zeros, odd number of ones. If you read zeros, it becomes even number of zeros and odd number of ones. Even number of zeros, odd number of ones is Q1. Next, Q3 for 1, that is odd number of zeros, odd number of ones. If you read 1, that means ones becomes even. Odd number of zeros, even number of ones, that is Q2. This is the transition diagram for DFA accepting even number of zeros and even number of ones. Q0 is the initial state. Thank you.